Welcome again. So in today's EPANET tutorial, we are going to learn how to perform hydraulic modeling or how to use EPANET software to model this kind of water distribution system. Okay, so before we even proceed, let me show you something. So let me select here at browser, let me select this browser, and for each link, let me select velocities. As you can see, these are the velocities values that we are having. Of course, they are within acceptable range, most of them. And again, if I select here at the unit losses, again, they are within acceptable range. Okay, again, most of them. And not just that, let me close this and let me select for each node, let me select pressure. And if you can take a closer look, especially at these end junctions here, you can see we are having pressure of this value. So from here, what we are having is 26, here is 31, here is 20, again here is 29. In a simple language, we are having pressure that is somehow not above 3 bars or above 30 meters of water columns. That is very important. So in this EPANET tutorial, I'm going to show you how to optimize your model just to make sure that you are having velocities, pressure, unit head losses within acceptable values. Okay, within acceptable values. Not just that, I'm going to show you how to use brake pressure tanks as a way of dealing with these huge pressures. Okay, so this is our BPT number 3. Again, this is BPT number 2, and this is BPT number 1. So not just that, I'll even show you how to come up with this kind of report, which is very good, especially when you are dealing with when you want to produce a report for your project. Okay, so if you're new here, my name is Engineer Lodrick, and this is Hydroinformatics Academy, a place where we discuss about how to use hydraulic modeling for smart and informed water decision. That being said, I'll see you in the next part of this video. Okay, so before we start doing anything, the first thing that we need to do is to make sure that our settings are correct. So to do that, what I can do here is just to go here to project, and I'm going to select defaults. So from here, as you can see here, we have like 3 tabs. Okay, so the first one is ID label, properties, and hydraulics. So for hydraulics, what I need to do is to set my units into metrics. So if you want to use a metric unit, then here is where you can set. Okay, so the first thing that we need to do here is to set flow units into the units that you want to use. So for me, I'm going to use liters per second. Okay, liters per second. So I'll just pick liters per second from here. So if you want to use empirical units, for example, then you can choose the empirical units like gallon per minute or the other ones. So for me, I'm just going to use metric units, and for that case, I'm going to select this liters per second here. The next important settings here is head loss formula. Okay, so we have been using Hazen-Williams for quite a long time now. So for this EPANET tutorial, I'm going to use das Westpac. Okay, that's Westpac. Of course, feel free to use Hazen-Williams if you want. So for me, and for this tutorial, I'm going to use das Westpac. Okay, so that is done. So the other units from here, I can just leave the way they are. Then I'll just go here to ID label, and again, this one is very important. I want to label my junctions with like junction 1, junction 2, junction 3, or J1, J2, J3. So from here, I'll just select J, then hyphen, and again for reservoirs, I'll just select R, then hyphen, and for tanks, if I have, so I'll just select ST, which present a storage tank, then hyphen. And again for links or pipes, I'll just select P, then hyphen. And again for pumps, I don't have pumps. And again patterns, I don't even have patterns. So from here, I'll just click OK. Again, this is very important step. I'll just click OK. So you can even set these units as defaults if you prefer. Okay, so I'll just click OK. So from here, the next step here is to draw our network. Okay, so this is the water source for our network is a river. So I'll just select this reservoir just to model a river. Okay, so in EPANET, we model a river by using a reservoir. Okay, so I'll just select this reservoir. Then I'll just insert here some few nodes, this one here and also this one, and again I'll just insert the other junction from here, and again the other one here, and again the other ones are in this region, and the another one also is in this region, and again we have some few water distribution points. So from here what we need to do is to insert other junctions in this region. So I'll just add the other ones in this area, and again in this area, in this area. I hope my space is going to be enough. Okay, so the other one here, the last one, will be located in this area here. Okay, so what I need to do from here is just to link my junctions with a pipe or a link. So for that case, I'll just select here add pipe. Then I'm going to link these junctions from here. So this, I'll just link them just like this. So I'll just select this one and I'll link with this, and again this one I'll link with this one, and also this one. So from here, just take this one and link with this, and again link it with this, and again this one, and this one, and this in this area I'll just link them the way just like this. Right, left click, then select, and again also in this area and in this area. Okay, left click and left click in the middle of this junction. So this is a simple network that we are having here. So our network is drawn already. So what we need to do now is to assign elevation data. Okay, elevation data, that is very important. So from here, what we need to do is just to select this. Let me select this one, and let me start assigning elevation data from here. So the total head here is 1400. Okay, let me push it in this area, and again for this junction here, J1, the total elevation here is 1360, and again this one here, elevation at this area here is 1330, and again at this area here, elevation here is 1310, and at this area here, elevation is 1307, and in this region here, elevation is 1280, and for this region here, let me check. I think everything is okay. So let me select this junction again. So let me select here elevation and assign it is 1300, and for this end junctions here, elevation here is 1280, and again in this junction, the elevation value here is 1270. So let me select, so for this one and also this one, elevation here is 1280. Let me push it a little bit, and in this area here, elevation is 1270, and in this area here, elevation here is 1250, and again for this one, elevation is 1245. Okay, 1245. So the next step is to assign pipe length. Okay, so for each link or for each pipe, we need to assign the pipe length. Okay, so from here, so let me start with this pipe here and assign it. Okay, so by default, EPANET is going to assign 1000 meters as a default value for length. We don't want this. We need to assign our length value. So from here is 263, and again this one here, the length here is 600, and again this one here, the length is 550, and again this one also, the length is 600. Okay, 600, and again this one here, the length is 618, and for this one here, the length here is 260, and this one here, the length is 250. This one, the length is 150, and again this one here is 200. So let me go to this. So this one done, and let me select this. So the length here is 218, and again this one here, the length is 250, and again for this one, the length here is 270, and this one, the length is 150. Okay, so for now we have done with our pipe length. We need again to assign the base demand. Okay, so the base demand. So in this end junction here, and also this one and this one and this one, we need to assign the base demand. So in this area here, the base demand here is 1.2. Remember, this is average base demand 1.2, and again this one, again the same value 1.2, and again this one here is 1.2, and this one here is 1.2. Remember, this is a loop area, and to assign the demand, we just take the total value demand. So we just take the total value and then we divide it by the total number of junctions. So the total demand around this area here was 4.8. So we just take that 4.8 and divide it by the total number of junctions in this area here. So let me close this and assign the other demand in this area. So this one here is 0.7, and again this one here is 0.35, and again from here we have another 0.7. Remember, this is in liters per second, and again this one here is 0.35, and again this one here is 0.7. okay, so far so good. We need what we need to do here possibly is to add some text. Okay, some text. So let me go here to text and add label. So this one here is a small town. This one here is a small town, and again this area here we have a simple distribution point, and again this one here is another distribution point. Just to keep things simple, I'll just call it a kettle trough. And again, let me click enter. And again, this one also is a distribution point or water point, and this one again is a kettle trough. And this one here is a primary school. So from here, what we need to do is to increase a little bit its font. So let's assume here it is that value, and again this one, and also this one we need to do the same. We also need to do the same, and again at primary school we need to do the same. And again this one is our source, which again we can term it as a river. And again we'll just do the same. Let me select the value here and increase its font to 11. Okay, so again for this one, let me increase a little bit its value to 11. So this is the situation that we have. So this is a source, this is a small town, of course this is a domestic consumption area, and again this here is a primary school, this is a kettle trough distribution point, and the same applies in this region. Okay, so the demand, we have assigned the demand already, so everything is okay. But remember, we are using the sequence pipe. So if I click one pipe in this area, you can see the roughness coefficient here is 100, which is possibly the values of Hazen-Williams. We are not using Hazen-Williams, and we are using das Westpac. So we need to assign here the roughness coefficients factor which are relevant to das Westpac. So to do that, you can even go here and assign the values from one link to another. So what I can do is to first identify the pipe material that I am using in my network. So here we are using GS pipe. Again, this one here is a plastic pipe. Okay, but for this area, again, we are using the GS pipe or steel pipe. Okay, so steel pipe. Again, this one steel pipe, and also this one steel pipe, except this area here we are using a plastic pipe. So from here, so let me select the das Westpac value. So let me select this as simple text. As you can see, for galvanized or cast iron, the das Westpac friction factor here is range within 0.06 to 0.3. So I'll just pick here the average value. So the average value here is 0.18. So I'm just going to use 0.18 in this area to present the GS pipe or steel pipe. And again, for this area here, we are using plastic pipes. So let me go back to my table here. As you can see, for plastic pipes, what we are having here is from 0.02 to 0.05. So I'll just pick the average value from here, or the middle value. So for that matter here, the average value here, or the middle value, will be 0.035. And again, in this area, the average value will be 0.035. And again, this one here, 0.035. And again here, 0.035. Okay, so we are going to do the same in this area. Again, let me assign 0.035, and again here 0.035. So to simplify things, what you can do, if for example here we want to use the same material for this one and this one, what you can do is to select a region area. So to select this region here, select the region, and then let me pick this region here. So from here, what I need to do is a simple action. So from here, I'll just go to edit and select group edit. So in this area here, I want to assign the pipes with a roughness coefficient of, remember here we are using steel pipes or GS pipes. I'll just select here the value of 0.18. Okay, then I'll click OK. Okay, so two pipes were updated, so this one and this one, if I'm not mistaken. So let me check again, and this one, as you can see, these are the value. Okay, so for this region here, let's assume we are using plastic. So let me select again the region and select from here to here, and then I will left click just to join this this and this. So let me select group edit from here, edit, then group edit, and then I'm going to assign for all pipes. So for all pipes, I'm going to assign the roughness coefficients to 0.035. Okay, it seems as though this pipe here, P10, is not, so I'll just assign manually. And again, for this area, again, let's assume we are using a plastic pipe. So let me select here 0.035. So for now, our roughness coefficients are well set. What we need to do, so what we need to do from here is to run our model. At least let's see what we are getting. Okay, of course we are having some errors, so let me click OK. So as you can see here, we have some negative pressure. So the next thing that we need to do is to see at which area we are having some issues. So let me right click and select options. So from here, what we can do is to select this notation. So from here I want to display everything, so these values except this one. And so and to let me change the flow arrow and select the field one. Okay, so let me click OK. So from here we have this and also this one and this one. As you can see, the arrow values here. So what we need to do from here, at least let me increase the font. Let me increase the font, Notion, then select the font. Let me increase a little bit this font, and also the flow arrow, let me increase it a little bit. So the arrow size to 6, then click OK. So for now we're having some good values here. So let me go here to browser. So this browser, and again let me select map and also select the pressure. So at each node I want to display the pressure. Okay, so you can see here we have some very big negative values, and this is an indication possibly the pipes that we are using, they are quite small compared to the demands or to the flow in these junctions here. So to counteract this, what we need to do is to change the pipe dia. Okay, the pipe dia. So let me start here with a P1 and see what I have in this area. So before we even start to change the pipe dia, let me select the links. So for each link I want to display the flow. So as you can see here, the flow here is this one and also this one here. Okay, so the flow here is quite okay. And again, let me select the unit head losses. As you can see here now, these are the unit head losses. So the idea is just to make sure that at least we are able to achieve acceptable values for velocities, for unit head losses, and even for pressure. Okay, so this is what we are going to do from now on, just to make sure that we have the acceptable values of velocity, of unit head loss, and also the pressure. So to do that, let me do this. So for this pipe, okay, so as you can see here, the unit head losses are quite high. So from here, what I can do is to select this pipe and let me increase the pipe dia a little bit. Okay, so let me show you something from here. Let me show you something from here. Let me go to help and select this topic here. Okay, so let me select this one. If we increase the pipe diameter, we are going to reduce the head losses. And if we decrease the pipe diameter for a given Q or velocity, then we are going to reduce the head loss. So the lower the small the dia, the higher the head losses, and vice versa. Okay, so the same approach can be seen in Hazen-Williams. So if we reduce the pipe dia, then we are going to have a big values of head losses, and if we increase the dia, then we are going to reduce the head losses, of course, for a given discharge. So from here, let me close this. What we need to do here now is to increase our pipe dia so as we can reduce the unit head losses or the head losses. So from here, let me increase a little bit. Let me increase it to 63 and see what we are getting. So let me click run, and so if I click run, you can see now the unit head losses have reduced significantly. So from here, let me increase again from 65 to 75. Remember, what you need to use here is the internal diameter. That is very important. So let me click run again and see what I get. Okay, so let me increase again from 75 to 90. Okay, so this is the value. Let me increase a little bit. At least we need to have the unit head losses from 5 meters per kilometers all the way to around 10, somewhere there. So for now we are having 20. So let me increase a little bit to 110. Remember, we are using internal diameter here. And again, let me click run again. So this is the value. At least for now, it's not bad. Let me check the velocity at this pipe. You can see now we have 0.8. And also let me check the flow. So this is our total flow in this pipe here, which is P1. So let me do the same thing for this P2, 3, and 5. So let me go back to unit head losses. So from here, what I can see, we have again this big number. So this indicates that for a given flow or for a given discharge, this pipe that we are using here is quite small. Of course, the value here is the default value, which is 12. So we need again to increase the values a little bit so as to reduce the unit head losses. So from here, let me introduce here 63 and see what we have. Okay, so at least now we are getting, so let me push it up to 75 internal dia and see what we are getting. Okay, at least not that bad. And again, let me leave it like this for now and see what we're going to get after dealing with these other pipes. So let me again adapt the same value. So from here, let me adapt 75. And again, this one also let me adapt 75, and again this one also 75. Okay, remember the roughness, they are just the same. So let me click run and see what we are getting. So these are the values. Remember, we are looking at unit head losses. So for here we have 7.9. okay, this one, but here we have quite a small unit head losses, which also indicate that we are possibly having a very small velocity. So if I click here velocity, you can see here the velocities here are quite small. So before we click anything here, just to increase the velocity, because what we need to achieve is a velocity is not less than 0.4 meters per second. But for now here at this P3 and P4, the values that we are having for velocity here are quite small. So you can see here 0.2 and here 0.2. Okay, so before we touch anything here, let me deal with these pipes again, then I'll come back to P3 and P4. So let me go back here to links. Let me select unit head losses and see what you can get from here. So from here, let me increase the value to 63. Okay, 63. Remember, the idea is to make sure that we achieve velocities and unit head losses pressure in acceptable value. So from here, what we are having is, let me change back to velocity. You can see here we have 0.2. Let me reduce this one to 50. Okay, we need to get a pipe dia that will give us the values that we want. Okay, so the value for unit head losses, the values for velocities, and all those stuff. So let me select here 50, and at least let me see what we are getting. At least now we are having 0.36, which is not that bad. So from here, let me deal with this area again. Okay, so here velocities for this P10 is 9.28. We need to reduce this velocity by increasing the pipe dia. So from here, let me select 50 and see what we are having in velocity here. So you can see now we have 0.5, which is good. And again, let me use the same value in this area. So in this area, let me use 32. Remember, this is internal diameter. Make sure that you are using internal diameter, not outside diameter. Let me run again. You can see now at least we are having this kind of values here. Okay, so here 0.4 as a velocity, and again here 0.87. So let me deal with this part here. Again, from here, let me select the internal diameter. Let me select 63. And again, this one, let me set it to 63 and see what we are having. And again, this one, P8, let me select 32. Remember, internal diameter, and here 32. Okay, so let me run my model and see what we are having. at least for now we don't have those errors again. So let me click OK and see what we are having in this region. So this is the values that we are having. So let me change the color. So to change the color here, you can go here to label, select this area here, and then left click. So this window here is going to appear. So what I need to do is to make sure that any velocity value that is less than 0.4 will be assigned with a red color. Okay, red color, and anything here will be assigned to purple. Let me select purple. Of course, you can change the color as you prefer. So for me, let me select purple just to make sure that we're having. So anything above 1.5 will be marked with a red color. Okay, red color. So from here, let me select OK. So as you can see, we are having some issues. Okay. So what I expected is in these areas here, this pipe here will be with a red color because it is less than 0.4, but it seems as though we missed some figures here. So let me put here 1, and again let me put here 1.4. Okay, and see what we're having. So for now, any velocities less than 0.4 will be marked as in red color, just like this one here. Okay, so at least for now we are having this situation. Okay, so if you can remember, we said that when we will come back to P4 and P3 here. So let me deal with this one. So let me select here 63, and again here 63. Okay, remember this is internal diameter. At least we need to make sure that we are getting a velocity value which is above 0.4 meters per second. Okay, so in this region, this is why we reduce the pipe dia to 63. And let me click run, and at least for now, okay, not that bad. And for this one, let me put here 50. Okay, let me click run. Okay, at least that one. So let me select again the unit head losses. Again, they are not bad. We are having 7, and again let me reduce this one to 50. Okay, just to make sure that at least we are having unit head losses and velocity in acceptable value. Remember, unit head loss should be within 5 meters per kilometers to 10 meters per kilometers. Okay, around that region. Even if we get outside that, but we need to have a value that is close to 10, around there. Okay, so let me click run again and see what we are having. So this is the situation that we are having here. But in this region here, this one is quite big. So let me click and increase it to, let's say 50, because this. Okay, so the demand here was how much? 0.7, and again here is so this one here was meant to be a distribution point, and this one here was meant to be a cattle trough. Okay, so here the demand here is 0.7, and again here the demand is 0.35. Okay, so let me click run and see if we can reduce this unit head losses here. Okay, so at least now, so far so good, we are having this value. Let me check the velocity again, 0.36, and again, so we are having the small value in this P8, P3, P4, and P13. Okay, so for now, at least we are having this situation. So let me push this around this area, and this one around this area, and also this one around this area. So this is the situation that we are having. Okay, so the next step here is to check the pressure values. Okay, so we have checked the velocities, the unit head losses. At least now we are having something which is not bad. But if you take a closer look in this region, especially in J7 and J8, you can see the pressure values here are quite high. Okay, but remember, this is consumption point, or this is a water point or distribution point, so we cannot have this pressure values here. We need at least to have like 10 meters of water columns all the way to 30 meters of water columns. So in a simple language, at least we need to have like 1 bar to 3 bars, okay, in this distribution point here. But for now, what we are having here is 143, 138. Remember, this is in meters of water column. And again, the same situation we are having here. Okay, so for now, at least as far as velocities, unit head losses goes, we are having very good values. But what we need to do is to deal with this kind of big pressures here, which is to find a way that we can deal with these values. But for simplicities, let's see how we can use a brake pressure tank to reduce this kind of pressure in this region here, in this regions. Okay, so let's find a way to introduce our brake pressure tank just to make sure that we reduce this pressure to at least 3 bars, at least 1 bar to 3 bar, okay, of water pressure. So from here, you can see around this area here, we are having like 83. We're having 83. So let's introduce here a brake pressure tank in this region here. Okay, so the elevation here is 1310, and around this area, what we are having here is this value here. So let me introduce a brake pressure tank. So to introduce a brake pressure tank, what we need to do is to introduce here a node and a valve. Okay, so let me show you how to do it. So first, I need to remove this link. So before I remove, let me copy its values, because if you don't record these values, then if you close it, then if you delete it, you're going to lose everything. So let me introduce here another node, another junction rather, and again let me redraw this link here. Okay, so this link, remember the length here was 260, and again the diameter here was 50, and again the roughness here was 0.035, of course, for plastic. And again, what we need to do is to introduce a valve here. Let me introduce a valve. Okay, so for this valve here, what I need to do here is to, let me double click here and select pressure regulating valve. So to model a brake pressure tank in EPANET, what we need to do is to use this pressure regulating valve. I think, yeah, pressure regulating valve, and just to make sure that this pressure regulating valve takes pressure to zero, down to zero. So we're going to set here 0, and again, so this 0 here indicates the pressure that we want to set in this area. Okay, so for brake pressure tanks, what they do is to take pressure down to 0. In the same situation here, we can use here a pressure regulating valve and set here 0, just the same values that we are having with our brake pressure tanks. So from here, let me select the fixed status to none. Okay, if I put here open, it's not going to work. Let me select here none and close. Again, the most important step here is to make sure that elevation at J3 and elevation at this junction here, which is J13, is the same. So the value here is 1310, and again we need here to have 1310. Okay, 1310. So at this junction here and also this one, they need to have the same value. Okay, so let me click run and see what we are having. I remember now we are having 1112. Let me see what we are having, because we are having some issues. Okay, negative pressure, whatever. Let me see what we can deal with, how we can deal with this. So the main issue here is A12 is disconnected. Okay, so let me see. Let me take it to 63. I think this is what we are having. So this one, let me take it to 50. Again, the same error. Okay, and again this one. Let me put it open and see what I'm getting. Okay, so if I set open, it seems as though we don't have any issue. So if I put here to none, okay, just to activate this value I set here to none, then we are having some issues. Okay, so it seems we are having some issues with our valve. So what we need to do is to make sure that our valve is drawing in that direction of flow. So from here to here, and not from here to here. Okay, so from here, what you can do is either to right click and select reverse, or if that is a long process, you can even delete it and redraw again. So let me draw it again. Remember from where our water is coming from, so from J3 all the way to J13, okay, and not from J13 to J3, because that's not gonna work. And let me double click again and see what we are having. So from here, let me set the diameter. Okay, so let me leave the diameter the way it is. Remember, we want to take a pressure down to 0, because this is what our brake pressure tank is going to do in the real world. So we are going to set here 0, which indicates the pressure, and again the status here we need to set it to none. So if we set here to open, that indicates that this value here is open. So in a simple language, it is open. Okay, so if I set none, this value here is going to work according to the values that I assigned in this setting area. So for now, let me select none just to take pressure down to 0. Let me run. So take a closer look here. So initially, okay, so now we are having this value, which is 39, which is equivalent to 3 bar. Okay, so if I click here again, let me take the diameter to 50, at least the same value as this pipe P13. Let me set here 50. Okay, let me click run. So what if this valve here, so this valve were not here? So if I set here open, you can see the pressure in this region. You can see now the pressure here is 112, which is 112. Okay, but as soon as I introduce this PRV, you can see, or pressure regulating valve, you can see if I set here none. Okay, so as I said, if I set none, I'm going to command my valve to operate under this pressure. So let me select none. Again, this is what we are having. Okay, so you can see now I don't have 112 again, 112 as a pressure. So for now I have almost 3 bar, which is 30 meters of water column. So I'm going to do the same thing in these other junctions here. Okay, so in this area here, what I need to do, so now my valve here is done, which is valve 1. Everything now is okay in this area, of course, after introducing this valve. So what I need to do here again is to work on these areas here. Of course, I can introduce a brake pressure tank around this area and also around this area, but I think it is not going to be a good idea. Let me introduce a brake pressure tank around this area. Remember, at J4 here we have this elevation, and again at this area we are having this elevation. So what you can do, let me see. So here we are having 12 3007, and again here we are having 1280. So if I introduce, so in a simple language, the elevation difference between this junction here and this ones, it's like 27 meters. Okay, so let me introduce a brake pressure tank in this area. Again, we need to do the same approach. Let me select this. So for now, let me delete this pipe. Okay, let me delete this pipe. And again, I need to add another junction. So you can put a junction here, but it will be not because of space. Let me introduce another junction in this area. Okay. So let me redraw my pipe in this region. Okay, and again let me insert the value. So here we had a 250, and again here the internal diameter of pipe was 50. So the diameter was 50, and here we had a value of 0.035. Okay, and again remember, from this point to this point I need to introduce another valve just to model the brake pressure tank behavior. Remember, you're going to draw from where our water starts all the way to where our water ends. In a simple language, you need to draw your valve according to flow direction. So let me introduce this one here, and again let me double click it, and let me give it diameter the same as this pipe. Then let me give it 50, and again the settings here is 0. Let me put here 0, and again status, let me put here none, just to command it to use these values. If you put here open, meaning that it's not even exist. Okay, so for that case we also need to make sure that elevation at J4 is the same as elevation at J14. So the elevation here is this one, and also we need to use the same value in this. So 1307, so here is 1307. Okay, so now at least everything is okay. Let me run and see. So for now we are having 10.5, and here, okay, so 105, and here 118. And let's see, after introduce here a brake pressure tank, what we are going to have in this end points here. So let me click run. Okay, so at least for now we are having these values. Okay, so this one here is 20, and again this one here is 33. Okay, so that is how we are dealing with this big pressure in reload and also in EPANET. That is very important. So we are going to use the same approach in this area. So we need to find a good place to introduce our brake pressure tank in this branch here. So as you can see, the elevation at this point here is 1330, and the lowest point here is around 12. Let's assume 12. So the difference in elevation is 80. So if we put our brake pressure tank around this area here, it's not going to have a big impact in these areas. And what if we select this junction J5 at least? So let me see if I introduce in this area here what we are going to have. So let me do a simple calculation to see the difference in elevation. Okay, so in this area here we have 1280, and the lowest points here we are having 1250, so minus 1250. So according to this simple calculation, so if we introduce here the brake pressure tank around this area, what we are going to have here is at least 30 meters of water column. Okay, 30 meters of water column. So, and this is what we are having. Of course it can be less because of head losses, but at least this is what we are going to have. Remember, I just take the elevation difference in this point. So the elevation difference between this point here and the lowest point, and I get 30. So previously what I got, so if I considered J2 and the lowest points here, I got 80. So introducing a brake pressure tank around this area is not a good idea. So I'm going to introduce a brake pressure tank around this area here, around this area. Okay, that is very important, just to make sure that we are getting that 30 meters of water column. Okay, not above 30 meters of water columns. Okay, so let me again the same approach. Let me delete this, And let me introduce another dummy junction. Of course, you can just put here, but because of space, I'm going to introduce it somewhere here. Okay. Now, what we need to do is to redraw our link or our pipe. Okay, so from here to here, and this link had a value of 260, if I'm not mistaken, 260, and again the internal diameter here was 50, and the roughness coefficient here was 0.035, and again we need to introduce a valve here. Okay, so let me introduce our valve. Remember, this valve here is pressure regulating valve. Okay, because we don't have brake pressure tank in our EPANET, but this value here will just model the same behavior of brake pressure tank in EPANET. So remember, the intention of brake pressure tank is to put the pressure down to 0. Okay, and this is what we are going to set here. And again, we need to put it fix the status to none, just to make sure that we are commanding our pressure regulating valve to use this value here. So if I put here open, it's not going to work. So let me select here none, and after that, let me introduce here the diameter. So the diameter, let me adapt this pipe diameter here, which is 50, and again let me use here 50. Okay, so from that, let me run my model. Remember, for now we are having this value 138 and 142. Let me see, after introducing this brake pressure tank, what is the values we are going to have in this J7 and J8. Of course, we are having some issues. Let me see, we are having some negative values after introducing this valve here, but okay, so the mistake that I made here is that the elevation at this point here is not the same as this one. So I need to make sure that elevation at this J5 is the same as elevation at J15. So let me take this value, which is 1280, and introduce it in this area here, which is 1280. So let me run. So this is what you are going to get if you don't, if your values are not the same in these junctions. So at least for now, we managed to take the pressure down to 26, and this is 31. So it is around the areas that we want our pressure to be. Okay, remember, pressure needs to be at 10 meters of water columns up to 30 meters of water column. Again, just remember, some other manuals, they even recommend to have 5 meters of water columns. Okay, so just to keep things simple, I'll just adapt 10 meters to 30 meters of water column, and this is what we're having. Okay, so at least for now, after introduce a brake pressure tank in our EPANET, now we managed to take pressure to reduce the pressure to pressure which is required in these areas here. Okay, so so if I keep here on open, so I fix the status to open. As you can see, this is the pressure that we're having. So as soon as I introduce a brake pressure tank by setting the status here to none and put here the settings to 0, this is what we are going to get in these areas. Okay, so that is it. So for now, what we managed to achieve is that at least we are having required pressure in these areas here. Okay, in these areas. So here is 2631, this one is 2033, not that bad, this one is 29. Okay, so this is what we have so far. Okay, let me go back and select unit head losses again. It is good, as you can see here, not that bad. Again, for velocity, again, not, it is okay, even though we are having some issues in this link, this one and this one, but it is not that bad. So the flow, this is what we have. So far so good. We have managed to deal with velocities, unit head losses, and pressure. The next thing here is to do simple stuff, just like so. Let me click run again. At least now our model is okay as far as steady state analysis goes. At least now our model is okay, but let's ask ourselves a simple question. So now we are having some negative values here. Again, here we are having some negative flows. Remember, this is a flow. Now we are having a negative flow. So what we need to do to remove these negative flows is to just right click this one, and okay, so let me click and right click, then select reverse and run again. You can see now the negative disappeared, and also this one, do the same, reverse and then run. At least now we don't have negative values again. So remember, among the benefits of a loop, of a grid or loop water system, is that even if one pipe here is broken, then water will find another way to supply water to this area. So let me put it in a simple language. Let me assume this P2 is broken and it's not work. Will water flow to this area? Okay, if we have a major breakdown in P2, will water be able to flow all the way to these areas? Okay, so let's see what we are getting. So let me select here and click properties, and for this one, let me put here closed. Okay, let's assume that this pipe here is closed and no water is flowing in this pipe. Okay, so let me click run. Okay, so for now, what is going to happen is that even though this pipe here, okay, so let's assume that we are having here a major breakdown and this pipe here is not even work. So water is going to flow from this P3 to P4 all the way to P3, and then it will move to this direction. Okay, direction. And again, if for example we close this P2 and also we close this P5, what is going to happen? Okay, and again, that is very obvious, because if we close this one and this one, in a simple language, water is not going to flow in any direction. So let me put this one open. And then click run. At least now our water is moving in this direction. So this pipe, if we have a major breakdown here, we are very confident that water will be able to flow so we are very confident that our network will be able to supply water to these areas here. Of course, water will come from our source all the way to P5, P4, P3, then to this section, and P5, P4 to this section, and P5 to this section here. Now let me open it again. Let me click open and then run. Okay, so we need to ask ourselves, so what if we are having a major breakdown in this P3? Will water be able to flow to this point here? So let me right click and select properties and select close. Again, we don't have any issue, because even though this pipe here is not working, or we have a major breakdown, water will flow from our source all the way to P3, P4, and all the way to this area here. Okay, so let me close this and click open. And again, what if this one here is closed? Okay, so let me close this before then and see what we are going to have in this. So let me close this. So even if this P4 here is not working, or we have a major breakdown in P4, then water, it will be simple for water to run from this area all the way to P5 and supply water to this primary school. And in this area, water will be flowing from P2, P3 all the way to this area here. That is very important. Okay, that is very important. And again, let me put it, let me open it. But what if this pipe here is broken? This P6, will water be able to flow in this area? The simple answer is no. So in a simple language, this is the benefit of using a looped system in your area. At least for now, our model is okay as far as steady state analysis goes. Okay, at least for now, our model is kind of okay. Let me click run again. At least this is what we are having. So if I select velocities, of course this is what we are having. So if for example I close this one, I remember for now we are having 0.3 and 0.4. If I close this pipe, you can see now the velocities that we are having in these areas here. So if this pipe here is not working, this is the situation as far as velocities goes. Okay, so let me again put it let me open this and let me click run again. So you can see if we don't have any issue at P2, this is what we are having. So let me close this P5 again. Let me close this. Again, this is the situation that we are having. So for now, at least we are having these values. Okay, we are having these values. Pressure, velocities, unit hair losses are quite okay. So what we can do now is to print a report. Let me print here a report. Okay, so you can just click a report and then click full report. And let me save somewhere. Let me give it a simple name. Let me call it a looped network report. Remember the location is in let me put it in a desktop. Okay, so let me go back to my desktop. Of course this one is a looped network report. So let me right click and open it with Word, Microsoft Word. So this is our network. Again, these ones are the nodes, start and end nodes, and this is the length, and so every values is here. Remember, if you see the valves, this indicates the brake pressure tanks. Okay, so this is our report. So for velocities, these are the values. Everything now is okay. So if you are new here, just make sure that you subscribe, and if you get value out of this video, again make sure that you just click that like button. So that being said, I will see you in the next video. Thank you.